Alright, so here's a problem, a frame problem. This is kind of a neat frame because you'll notice it's only got two elements, so we'll have not a lot of work to do. It's got a fixed connection here at A, it's free in here at C, and this is a rigid connection at B. And we want to find the vertical displacement and rotation at C. I don't know if I'll have time to do the rotation, but we'll definitely do the displacement. And what's unique about this one is I want to have the effects of both bending and axial force. So when I start going through the structure and finding my internal forces, I'll find the moment and the axial force and get them at the same time. Okay? So remember, with virtual work, what are we going to do? We're going to find the moment and axial forces due to the real loading, which in this case there's a horizontal load here of half a kip per foot, kind of a wind load. And then out here there's a point load of 10 kips. We don't need all this information, but we will need E and I and A. We won't need G and K. That's for something later on. We'll talk about that a bit later. So let's talk about a strategy of how we're going to proceed. So let's start first with, I'm going to cut this structure somewhere here between A and B. And how do we want to... What side are we going to look at? We're going to look at this side, say the upper side, or the lower side?
Lower.
Everybody want to do the lower side?
Yep.
I say no. Why do I say no? I have to find all these reactions just to get started. That's three equations I have to solve for. I have to find the moment, the shear, and the horizontal force. What if I just stop and do the top side? Can I write an equation up here? Yes, I can. So I think I'm going to go this way. Now when I cut here, I don't think you'll have as many misgivings as before. You want to work this left whole side or this little short right piece? I think you see the right piece is probably easier. So in both cases, I'm going to go towards the cantilever to find my moment. So I won't have to find any reactions here. I think that saves you a little bit. Also remember that in this particular case, I can choose my origin any place I like. Okay, so let's think about the moment and axial stuff here at what I call AB. So let's look at section AB. As a starter. So I'm going to draw my free body diagram of that section. Something like this. And I know up here on this end I've got the 10 kip force. I know this is 10 feet. And then internally I'm going to assume that I have a bending moment and an axial force. So this will be the force, I'll say, in AB, and this will be the moment in AB. And I've assumed kind of positive values for both of those. I think it's going to be a lot easier to measure everything in this direction. Oh, I've left off my force. I messed up. Let's see if I can recover. So I'll do my distance in this direction. I'll call it Y, and then I'll kind of cheat and turn that into a distributed force, and I can turn that into a concentrated equivalent force. What would that be? Well, it's a rectangle, and it's going to be the length of the rectangle times the height. The height is 0.5, and what's the length? Y. So this should be 0.5 is really 2, so this will be Y over 2. You want to see that? And the distance from wherever I cut it, say the center here, will also be Y over 2. That's all we need. So now if I come over here and sum the moments at this cut I've made in AB, make sure it's in equilibrium, what do I get? Well, here, using right-hand rule, this moment that I've drawn is negative. The moment produced by the force y over 2 is also negative. So there's y over 2, that's the force. And what's the distance from the cut to the centroid? Y over 2. And then I get all the way around to the 10 kip force. That's also creating negative moment. And that has a moment arm of 10. Everybody see that? So now when I look at my moment in AB, really now it's going to be a function of y, is going to be equal to negative y squared over 4 minus 100. And that will have the units of kip feet. Now in this section, do we know the moment anywhere? Unfortunately, the answer is no. If I had a reaction at A, then I could say at y equal 20, that would be the value. And if I also found the internal moment at B, I can put in y equals 0 and find it. I will let you know that if you do think of just this part of the structure, and you want to know the moment at B, what do you think it's going to be? Well, it's a length of 10 and only has one force of 10. It's going to be 10 times 10 is 100. And you'll notice that when y is 0, I do get 100. So it looks pretty good so far. And that's a fairly manageable equation for the moment. Everybody okay with that? So while I'm here, I'll go ahead and pick up the force, my real force, and I'll get that just by summing the forces in the y direction. And when I do that, I have my force in AB going down. That's negative. And the other force I have is 10. It's also down. So it looks like the force in AB is minus 10 kips. So AB is in compression. Do I care about the shear here? In this problem, no. So I don't have to account for the force in the x direction right now. I will tell you that later on we will talk about the additional displacement generated by shear, and then we could pick that up too. So you'll end up, you could have displacement energies from all three of the components we do in 2 dimensions. Okay? That's probably the hardest one of the whole thing, because the next section that we would do would be the free end, which is section BC, and I think we've seen free bodies like this quite a few times. So there's the structure just to the right, and on the free end we have the 10 kip force, and then internally I would have the tension force in BC and the moment in BC, and those are both positive the way I've drawn them. And then I get to decide how I want to orient that, and I think I'm going to make it easy for myself and just say, hey, it goes this way, and I'll call that x1. So when I sum moments at this cut, the cut between A and B, and make sure it's in equilibrium, what do I have? Well, internally the moment with my sign convention is negative. And then the moment about the cut due to the 10 kip force is also negative. And it has a moment arm of x1. So that's easy enough. The moment at BC is going to be negative 10 x1, and that'll have the units of kip feet. We can check that one. We know that the moment at the free end is 0. So in this with this coordinate system, that's x1 equals 0. And you see when x1 is equal to 0, I do get 0. And also when x1 is equal to 10, that's point B, it should match the equation that we had here when y was 0. It's the same point. So you see when y is 0, I have negative 100. When x1 is 10, I have negative 100. So it matches. So I'm feeling pretty good now that these moment expressions are good. And then while I'm here, I want to find the axial force. To do that, I'm going to sum forces in the x direction and make sure I'm in equilibrium. In the x direction, you can see all I have is BC. So I'm not really going to worry at all about the axial contribution to the displacement due to BC. It's okay? Any questions about that? I think the only thing that's a little different for us is the fact that you can start choosing the sign, the origin of your signs and the direction, whichever is convenient for you. Now, once I've done that, I'm stuck with those, right? So when I look at my virtual system, what is it going to be? Well, first of all, I have the same structure, same geometry. Got this cantilever-looking frame, fixed connected at A. And I want the vertical displacement at C. C is here, vertical is up and down, so I'm going to assume down, and there's my force. This is 10 feet, this is 20 feet. So I'm going to do the same two free bodies I did before, except this will be the only force I'll consider. So for the virtual system, let's start with section AB. And since I've already made this assumption of how things are going to behave, I'm going to do the same thing here. So here's pretty much the same free body, except I just have the one virtual load here. It's still 10 feet off. I'm still going to measure the y direction down. And I'm still going to have a virtual force, which I'll call lower f AB, positive. And I'll have my virtual moment, lowercase m AB, also positive. They have to be in the same system as I chose before. So now what do we do? Guess what? We're going to sum moments of the cut again. We have never done that before, so this will be a new experience for everyone. So let's do it. So let's sum moments at the cut. Again, I like to use right-hand rule, so we'll do that. And we'll make sure everything is equal to 0. So when I do that, all I have is the moment due to the virtual system, that's negative. And then the only other force on the system is this, minus 1, and it has a moment arm of 10. So it looks like my virtual moment at AB is going to be equal to minus 10. And it's going to have strange unit, feet. Because remember, the force unit is dimensionless. And we're going to match this guy up, the minus 10, with the real moment, and then we'll integrate that over y. And then we'll go to the next section, which will be section BC. And again, we've already established a coordinate system and a free body diagram system, so we're going to use it again. Except our virtual load on that system is 1. We've already chosen a direction, so we're going to use the same one. Except interior, we would have the virtual force in BC and the virtual moment in BC. One thing to remember is the real axial force in BC is 0, so it's really, we don't even need this one. But you'll find out that it's also going to be 0. So even if there were a real force, the virtual force would knock it out. So again, we'll do the same thing. We'll sum moments at that cut and make sure we're in equilibrium. And what is that going to give us? It's going to give us a minus or negative virtual moment at BC, and then minus the force, which is 1, times its moment arm, which is x1. So when I solve for the virtual moment at BC, I get basically minus x1. So from my perspective, you've done all the hard work. You've got the real moments for the system and forces. You got the virtual moments for the system and those forces. Now we just need to write the two virtual work equations, one for bending and one for axial force. So I'm going to need a new page here. So let's flip this one up. And let's start with the displacement at C. So what we're going to do first is we're going to integrate AB. So we're going to integrate from A to B, the real moment, the virtual moment, divided by EI. And I believe in that particular case, we measured everything from the top down. That's going to be dy in this case. And then we'll have another one where we integrate from C to B, the moment, the virtual moment, again divided by EI. In this case, I think the dummy variable was x1. So we're just going to fill in the bits and pieces here for that. E and I are constants, so I'll factor those out. And in the first one, the distance from A to B is 20, so the actual integral is going to be from 0 to 20. So let's recall that this is my real moment. Again, we're measuring y from the top down, so it's going to go from 0 to 20. So it's going to be minus y squared over 4 minus 100. So there's my real moment, and the virtual moment for the same system is just minus 10. And that will be dy. Then we'll add to it the integration of BC, which has a length of 10. And the real moment for that system is minus 10x1, and the virtual moment is just minus x1. So I'll have minus 10x1 minus x1 and integrated dx1. And you see, if we had enough time, this would not be a very challenging integration to pull off. But I'm just going to say that's good enough for me today. I may, when I publish the written version of this, in fact, I may leave some space right here, and I'll finish it up in the office and publish you the numerical solution. But for me, that's good enough. Now, is that the total displacement at C? No. So this would be the displacement at C, really just due to bending. So let me come down here and say, well, what would it be for axial? Well, remember for that, we're going to sum the real force, the virtual force, times the length divided by AE. And what would that be? Well, let's look back. The real force in AB is minus 10 times the virtual force in AB is... oh, I forgot to do it, didn't I? I forgot to get it. I did, didn't I? Oh, let's go back and do it. So we need to sum forces in the y direction here, assuming up is positive. So I have the virtual force acting down and the actual virtual force. So that's not hard. So it looks like the virtual force is minus 1. Sorry about that. So when I put this together, so I'll have the real force minus 10 kips. The virtual force is minus 1. The length of AB, which is 20 feet, which is 240 inches, right? Is that right? So 240 inches, and then I would divide it by A and E. And A is going to be in inches, and E is in kips per inch squared. So all the inches are going to be a workout. Now, this is the section for AV. What about BC? Well, if you look back at BC, the real force is 0, and same thing would happen here. The virtual force is 0. So there is no more contribution. That's it. So let me just pencil this in. So, oops. So this is the real force in AB, and this is the virtual force in AB. This is the length, and then of course AE. Up here we had the real moment, the virtual moment, the real moment, and the virtual moment. And then both of those will be divided by EI. When I get the numerical values, then the total displacement at C would be the bending component, and then we'll add to it the axial component. So when I get back to the office after class, I'll go ahead and finish this up, get a numerical value, compute this and get a numerical value, add those two together and put that result here. But that's really, from my perspective, that's all you have to do if you had a problem like this on the exam. So any questions about that? I think it's a very doable problem for the exam. It's not that tough. Okay.